Okay. Right. Okay, let's get started. Thank you, Jeff. I don't think Jeff needs an introduction anymore. In this to this audience at least. Are you still at Ames, Jeff? What is your
Oh,
how do we introduce you actually?
well, I'm retired from
Right.
NASA completely, so I'm a free citizen basically. I tried to find out if NASA wanted me to keep like on papers that I write. Do they want me to keep the affiliation? And I couldn't get an answer as usual, so I just say NASA Ames retired on the bottom.
Ah.
I haven't been on the campus at Ames for many years, well, several years now. So
Oh. Okay.
no, I find I'm working in some sense more intensely now that I've retired than I did before, if you could imagine. But anyway,
All right, good. So Jeff will be talking about double periodograms and potentially extensions to Bayesian blocks and Lomb-Scargle periodograms and several other things. Arrow of time sounds interesting. We'll see how far along we get. If we need more time, we can always do this again next week. So take it away, Jeff.
okay. I hope can you see my slides full screen
Yes.
and the cursor is visible?
Yeah.
Okay, well, I sort of tricked Vinay. This is really a self-serving advertisement for the book that I'm writing. It's to come out there's a series that Cambridge, and this is the Cambridge in England, I should hasten to point out, Cambridge University Press. They have a series of, when I first signed up, they called it handbooks in observational astronomy, but I guess they've changed the name to handbooks for research astronomers. Anyway, hopefully, and maybe early next year, it'll come out in that series. And basically, what I wanted to do initially was to talk about some of the new things that I developed in writing the book. When I first started, I thought, oh, this is straightforward. I'm just going to regurgitate papers I've written and paste them together with some nice wordsmithing and so on. But I kept finding new things to do, and the bullets on the right are a list of I think they're the major things that are kind of new. I'm just curious. Do any of you get the in the red shameless commerce division? Does that ring a bell for anybody in the audience?
Our talk.
Yes. Okay. Good. Uh,
Yes.
I, for those of you who don't know, there was a great show that I guess was produced in. They pretended like it was in Harvard Square or something, or
Oh no, they really did. I think they had an office in Harvard Square, right? I mean,
Wasn't it? I thought it
Yes,
was in Canada
I
Square.
think so. I think
Maybe.
so.
yeah, yeah. No, they had they still have an actual
Garage.
garage somewhere in Cambridgeport. I've never been there, but
oh, okay, great. Well, I loved the show, and they always had this funny stuff at the end and selling stuff, and they're shameless. Anyway, um, uh, let's go on. Just to, I guess, a rejoinder to what Vinny said. I guess I don't need to introduce the idea of hunting for periodicities to this audience. It's one of the major things that astronomers do. It's a little bit like the lamppost and the lost keys or something. It's an easy thing to do, so people always do it. So there's a whole industry. The physics is sort of generic: rotation, oscillation, revolution, orbital revolution, and even wave motion are some of the ways that periodic signals can be generated. And so on the periodogram is quite old. It's Schuster invented it in 1898 as explicitly he called it a tool to find hidden periodicities, and hidden in noise is what he meant. And the problems with it are well known. I like to separate the problems into statistical problems, and I couldn't find a good name for it, but subjective sort of background generic problems. I'm curious. The second bullet or the second statistical issue is that the periodogram or the power spectrum itself is noisy and it has a lot of peaks in it, and especially at low frequencies in AGNs and so on are very confusing. I once amused myself by trying to figure out how many local maxima there are in the periodogram of white noise. And numerically, I convinced myself it was exactly n over 6, where n is the length of the data set. Is that a well-known thing in statistics, or is it true, or does anybody? It's just a curiosity, but
Sorry,
okay.
I've never heard of that.
I assume there's some way to prove it from I don't know analysis, but I just did it.
There's a lot of work even in astronomy on the statistics of Gaussian random fields in 2D. You know, how many peaks are in do you expect in the background of a noisy image if there's just white noise? Alex Gillet worked on this for cosmology and also for some image detecting work, source detecting work that I did with him and Tomasz Budovari. So there's, I bet in that literature, you might be able, I don't recall ever seeing anything in 1D, but you might be able to find something there that could be worked out.
Well, it's just kind of a fun thing to point out to the period hunters who think they found a wonderful period in the noisy data. But anyway, I've come to believe that in most practical situations, the nuanced statistical issues that everybody obsesses over about sigma this and 4 sigma that and so on are almost never really the limiting factors and the important things. The important things are the things at the bottom, the generic, dealing with trials factors. It's a statistical issue, but deciding what are the actual trials that you should use is a subjective thing, and you know, depending on ahead of time what was your hypothesis ahead of time. Was this an exploratory analysis? And anyway, I don't want to go on about this, but I only believe I'm almost gotten to the point where I like the quote usually attributed to Eddington that if you need statistics, you should do a better experiment or something like that. So I kind of expected to be cut off when I said that in this group. But anyway, okay, here's a kind of an overview of the one-dimensional periodogram, the Schuster periodogram and the Lomb-Scargle periodogram. I learned a few things that I should have known, but I didn't quite realize when I worked this out. Namely, that if you just start with the obvious least squares or residual minimization and grind away, if you don't do the, well, let's look at on the right-hand side, there's what I call the Lomb trick, where you decide that you don't, you want to make the sine and the cosine orthogonal, so you get rid of a term in the residual, and it simplifies things. It's a nice trick, and it leads to this periodogram that a lot of people use. But if you don't do that, you get something that isn't quite the original Schuster periodogram. The Schuster thing is down here. It's simply essentially plugging the samples into the obvious expression for the Fourier transform and not caring about the fact that the times are not evenly spaced. It's a useful thing in some contexts, and I think there's some people have used it in astronomical contexts, but I was kind of curious that you get something similar to Schuster, but these denominators are the same as in the Lomb-Scargle thing. Oh, wait a minute. Whoops, sorry. Maybe there's a mistake here. Let me get, why is the thing on the left? Well, it isn't, well, forget this. This may be wrong. Anyway, so this is sort of the background for the one-dimensional case, and I don't want to spend a lot of time, but the on this periodogram, but I don't know how well known it is. There's an expression for a Fourier transform that you can derive the LSP from as just the absolute square, and it's a useful thing.
By the way, Tom has a comment.
Sure, go ahead, Tom. Please interrupt.
No, I didn't want to interrupt. It was just a side remark, but I believe the Lomb trick is just computing the profile likelihood, the log of the profile likelihood for the frequency. So to connect to statistician lingo.
Oh, I see.
I thought it was all profile likelihood. It's just a question of whether or not you orthogonalize the terms in the regression to make the regression formulas easier.
Yeah, I think the orthogonalization process is what comes out of profile likelihood. It's from plugging in the best fit
Well, you can
phase.
orthogonal. I mean, you can profile regardless of whether or not the coefficients are orthogonal.
Yeah, I think it probably doesn't actually. I'm probably not quite correct. It probably doesn't actually profile. It's probably a plug-in estimator.
Yeah. Or maybe it makes the profile more interpretable because it's more orthogonal.
Mm-hmm.
Anyway.
Okay, thanks. That's great. I didn't realize there was that connection. Anyway, here's a I don't know what to call it, the Lomb-Scargle Fourier transform, but it's an expression that I kind of derived in an ad hoc way, but it's useful. It's a Fourier transform, and playing around with it, you can transform data, and it's invertible. You can do an inverse transform and recover the data, and have to be a little careful about the frequency range and the effective Nyquist frequency and all that stuff. But I think it should be more well known or used in astronomy because it opens up a lot of possibilities for other things you can compute for unevenly sampled data, like cross correlations, or I don't know if anybody's familiar with the New Star has a dual focal plane. There are two statistically independent focal planes, and they invented something called a co-spectrum, which is essentially the Fourier transform of one of the data streams and times the complex conjugate of the Fourier transform of the other data stream. And they developed it in order to deal with instrumental issues, pile up and dead time and so on. But you can use this Fourier transform at the photon level. You can calculate the co-spectrum of new star data. And by the way, we're doing this. I should introduce electronically, I guess, Sarah Wagner, I think, is on the line here, and she's the lead author on a paper on an AGN where we actually show this for some new star data for a gravitationally lensed AGN, which is a very interesting case. I'd like to point out one of the things I'll mention later. The LSP is often criticized because it doesn't include weights and stuff like that. Well, I have some comments about that, but in fact, this includes weights, and it's interesting that the weights have to be applied to the trigonometric terms, the denominator and this Lomb arctangent formula. So it's not simply a matter of slapping weights in front of the measurements. And I don't know if that's maybe Tom or David or somebody will tell me that's some well-known result for general situations. But anyway, that's weights can be applied, and they're easily built into everything I'm going to talk about for the double periodogram. And like I said, this can be used at the photon level, And I love to show this example because it's just from Fermi. I just grabbed a few, I think it was a few tens of thousands of photons, time-tagged photons from an AGN 3C279. And here's the power spectrum, the absolute square of the formula I showed on the previous slide, as a function of frequency. And I first looked at it and said, oh, great, this is the typical power spectrum of all AGNs. There's a 1/f colored noise component that drops into the noise floor, and it's noisy because the power spectrum is noisy, and this is photon data and so on. But then I wondered about these peaks. What are these big peaks, and what's going on here? Well, it turns out those are all real peaks. They're real in the data stream, but they're not real for the source. They're all artifacts in a sense of the orbit of the spacecraft. The three periods that stand out are the precession period. Fermi precesses at about 54 days, and that modulates the detection. It's typically a small effect. It's a small modulation, but since it is periodic, it shows up here. Of course, the orbital period shows up. The sidereal day also shows up. The vertical dotted lines and so on are maybe a little bit confusing. They obscure the peak, but there's a sharp peak at the sidereal. Oops, did I do something? Sorry. Yeah, well, here we go. And a little challenge. Anybody, and in fact, the resolution is good enough that it's well separated from the synodic day. Why in the world is there a sidereal day period in photon data from a spacecraft? And maybe I'll just leave that as a challenge unless somebody knows the answer. If you know the answer, don't say anything. But if you don't know the answer, think about it. I think it's kind of curious. By the way, maybe I should be monitoring. Are there some chats that I should? Tom has something about.
By the way, I should probably comment for the people who are new to CHASC talks. Feel free to interrupt and ask questions at any time. We pride ourselves on not letting our speakers finish their slides, so don't worry about it.
Yeah, thanks. So, okay, let me go on. And even more, not only can you see those three periodicities, but you can see harmonics of them and beat frequencies between those frequencies and the harmonics. So this power spectrum with just a little bit of data, it's a few thousand photons, that it didn't even matter that they came from a source. They just even background photons would have showed the same thing. And here's a hodgepodge of things. I hope I'm not insulting anybody in the audience, but this is what I call the great QPO hunt. This is just sort of a random sample of a small fraction of the figures from QPO hunting papers. I don't know what else to call them. People that grab some data, they think they see a characteristic wiggle in the light curve, and then they run a Lomb-Scargle periodogram, and it sticks out above some contour levels. What I'd like to put, and I'd like feedback to see whether I'm really off base on this, but I think all of this it's not useless, but what people do is they do a simulation. They do simulations with various degrees of sophistication and generate contour levels of the amplitude of the periodogram of the simulation of the simulated data, and then they see whether the actual periodogram sticks above those contour levels, and if it sticks above the 3 sigma level, they say, oh, we've detected a QPO at 3 sigma. Well, in a simulation, what you're trying to do is to estimate the frequency with which the thing that you have claimed to find or the thing that you're looking for appears in the synthetic data by chance. But that's not what these plots show. They don't show how often you find a QPO. They show how often the power is above some threshold. So it's like you're not really doing the right thing in terms of success versus failure. And so what should be done is something different. And again, the paper that I mentioned that Sarah is the lead author on makes a stab at doing something unusual in this regard for not the power spectrum, but the autocorrelation. In the gravitationally lensed system, the autocorrelation is the...
Can I ask a question there, Jeff?
Sure.
Could you elaborate on that concept that you mentioned? I mean, what is the difference?
Oh, okay. Well, okay. Why do you simulate data to run a 10,000 synthetic light curves and do the same analysis that you've done on the real data? You do it to see how often the thing that you have claimed as a real feature, or you want to decide whether it's a real feature, not a statistical fluctuation, how often does that feature appear in the synthetic data? Well, so what you should do if you claim to find a QPO, how often do I find a QPO in the data? Well, a QPO isn't just a high level of the power, it is a peak in the power. You could even think of it in terms of specifying the width of the feature. So when you make these plots, you're assessing something that's not the same as success versus failure in the simulation. I don't know if I'm not.
So you're saying that the test statistic shouldn't be the peak, the highest value of the ordinate of the periodogram. It's a feature that has some measure of structure in it as well.
Well, if I understand correctly, what people are not plotting is the highest level. They're just plotting the level. They're just doing the statistics on the power at each frequency. So they're not finding peaks. That's the point. They're finding high powers, but high powers and peaks are different things. That's the point.
Mm-hmm.
And in fact, if you look at it coldly, it makes the statistical significance, if you do it right, so to speak, the significance should be higher because you're looking at a sort of a constrained thing.
So this seems like it's also the answer to your n over 6, or it's the empirical version of your n over 6 number before. You're doing the same thing of looking for a peak in a 1D random field, so to speak.
Yeah, yes. But the right thing to do, I think, even something more than just a local maximum, it should be a feature that's consistent with being physical QPO that should have a shape to it, should have the right shape,
But is that what you're doing? Are you actually using shape, or are you just saying what's the power of a peak?
That's my point. But I'm not doing anything. These are all
I didn't know if you were involved in Sarah's paper. Maybe Sarah could weigh in.
Yes. Oh, sorry. No, and that it's sort of maybe we shouldn't. It's a little bit in the weeds, but it's something part way to doing a rigorous modeling of a peak. It's what we do is it's called the lower envelope thing. We subtract the lower envelope of the autocorrelation to get rid of the colored noise, and in that, when you do that, you're closer to having the simulation be finding a QPO. I don't know how to say it in words that.
So, I mean, but then that presumes that you know the shape of the QPO
Yeah.
beforehand, right? Before you detect it.
Um,
Isn't that harder? I mean, how would you, I mean, just to just to find a sort of a indication that a QPO exists, right? So how would you do that without?
Well, that's another sore point with me. Unfortunately, I have had to referee a whole bunch of these papers, and none of them discuss the issue of, well, I shouldn't say none of them, but it's very rare that anybody thinks about whether they're resolving a QPO, that it's a truly broad feature. Is the feature they're finding broader than the point spread function of the analysis? Are you finding a PO or a QPO? So people are, frankly, I think that it's not a scandal is too big a word for it, maybe, but the literature of QPO hunting is, I think, pretty, well, like I say, I hope I'm not insulting anybody in the audience, but there's just a lot of stuff that is turning the crank and doing things because previous people have done the same thing. That's why all of these plots, everybody else has done it, so I should do it.
Yeah, you can point to something in the literature. Can I just ask for just to help me understand, if you had a procedure, like a well-defined procedure, that was like, if this procedure leads to yes, there's a QPO, or no, there's not a QPO, and you applied that same procedure to your Monte Carlo simulations and your data set,
Yes.
then it should be fine. So the problem is the procedure as it's, maybe it's well defined for what they do for the simulations, but it's not.
Sorry, you faded out at the last. Can you?
Sorry.
David.
Sorry, David, you dropped out for a moment at the end.
Yeah. Well,
Sorry, I'm just.
Go ahead. Can you finish that question?
To tether to my phone so I have a better connection. No, yeah. So the question is, so what's different about what these QPO searches are doing that makes you unhappy about it? It must be that somehow the procedure that they're applying to their data is a little bit interventionist or subjective, or not well defined enough that you can just deploy it in the simulations. Is that right?
Well, the way I put it is the statistic that they're evaluating is related to the chances that you found a physically real QPO, but it's not rigorously the same. It's related to it, but you're not doing the right thing. You're not the thing you stated at the beginning is exactly right. If you have an objective procedure that says yes, no, there's a QPO here, or is there not a QPO here, and you applied that to the simulation, the fraction of successes in that would give you the false positive rate, straightforward.
Yeah. That's
not what's done here. The false positives are based on how often the power is above a given level. The vertical axes in these plots are the power level. And so a vertical slice through these plots, which are effectively three-dimensional color scale plots, but they just show a few contours. A slice through that would be the distribution of the power at a given frequency, which should be exponential for white noise, but isn't because there's colored noise and so on. But that power is not this. Finding a high power isn't the same as finding a QPO.
But so for the null distribution, they had to have done some kind of trials correction, or is what you're saying that you could use something like that to account for the fact that I'm just kind of thinking out loud, like is one way to address what you're worried about to say that there's a smaller number of effective trials because these peaks have a width that's larger than the nominal width for white noise, or stuff between peaks of white noise or something?
Yeah, I'm not that you're getting into the details of what the right procedure would be, and that's the way I phrase it. And
yeah,
I'm not. I mean, there are various things you can assume. Do do you want to say I've not only found a QPO, but I found a QPO whose width is X, Y, or Z, or something like that, or some other a QPO and it's a first harmonic, or a QPO and they're
So it sounds like you're saying there should be a test statistic that has nuisance parameters, and you somehow need your procedure needs to explicitly deal with that.
right. Yes, a fully approach to this, I guess, would do that, and I don't think anybody has even mentioned that as a possibility in this literature, as far as I know. I was trying to actually. I thought someone in the Harvard group did some work. Am I wrong? Is there a Harvard paper on QPO analysis? The one,
Not from CHASC.
yeah. There's one good paper that Daniela H.
Opencott.
is one of the co-authors,
Open cotton. Yeah.
and I forget who else in that group, that I think is as far as I know, the best paper on the topic of finding QPOs against colored noise, and that's the key problem. And I think it.
Doesn't Simon Vaughan also have some papers that try to do this in a sophisticated way?
I don't. I haven't. I don't know. But it would be great Tom, if you could ping us or me with some suggestions. Or I think this is a great problem that should be. I mean, QPO hunting is such a. I get a feed every night from the archive, and it's rare that there isn't one QPO hunting paper. And every single one of them shows a plot like this. And I believe only the ones where the QPO is so big and stands up above the noise so much that you can see it in the light curve. And anytime you're fussing with two sigmas and statistical nuances, to me, I think that, like I say, these other factors, and this is one of them, the sort of subjective factors in how you actually carry out the analysis. To me, those are almost always the limiting factors, and not the statistical nuances, I guess, is the best way to phrase it. But so, Tom, thanks for your comments. If there's a literature on this that I don't know about, I'd certainly like to hear about.
I dumped a reference in chat that's just I don't know. The title is about periodicity, but the abstract is about QPOs. And I looked at it a long time ago, but I don't know if Simon's done more since. He also has a review article, I think.
Have I done something bad by clicking?
We see your archive now instead of your talk.
How do I get out of this? Tom, what have you done? Let's see.
You can command tab back to your keynote, I think.
Yes, that's a good, but unfortunately this little Zoom bar is covering up. There we
There
go.
you go. There you go.
And Tom, are you okay if I forward all referee requests for QPO hunting papers?
Definitely not.
Forward them, but
I've actually never done QPO hunting myself, so I am not an expert on that.
Okay, here's another. Let's see. Here's another. The sunspot numbers. I'm puzzled by the fact that this is probably the best known data set in statistics as the sunspot numbers. Many statistics textbooks have an appendix with the sunspot numbers in it, and blah 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 and so on. Anyway, there's a huge literature also in astronomy, and I think it's really not known. And one of my objections for using it as a standard example in statistics textbooks is that there's almost certainly instrumental effects over time, that the way sunspots were counted and observed and so on has certainly changed over the several hundred years in which data have been taken. The data sets available try to adjust for that, but that's obviously going to be uncertain. So there there's almost, and maybe that's one of the points is that, but I've never seen that mentioned in textbooks. But and also nobody knows what's going on there physically in a real sense. There's a lot of theories and so on, but even what's the actual nature of the power spectrum of this sunspot data is various people have gotten different results, and it's not just a simple peak. Anyway, here's the a Lomb-Scargle and also a Schuster periodogram. I forget which one is which, with multi-tapering and so on. The one-dimensional power spectra with basically a peak at around the known solar cycle value, but some hint of a resolution into maybe two peaks or a couple of side lobes. And anyway, when you see things like this, you often see the two things at the bottom. The uncertainty and the frequency is the width of the peak that you get in the periodogram, and that the best resolution you can get in terms of separating two different peaks is determined by the width of the peak. And these are both wrong. I hope the first one is well known, but the whole point of the double periodogram is to show that the second one is also incorrect. You can do better. And I'll go quickly. There's a lot of generalizations of LSP that are floating around. I do this because the literature has a lot of statements about the generalized LSP, and it almost always means, I forget the authors, but there's one where an additive constant is thrown into the model rather than trying to remove the mean value or estimate an additive constant in a pre-processing step. I guess it's useful in some situations, but there are a lot of other generalizations, including a lot of work by Larry Bredhorst models where it's not just sinusoids, but damped sinusoids. And he did some really neat stuff with amplitude modulated signals and basis functions other than sinusoids, which we'll get into in a minute. But in fact, a very early paper, Barning in 1963, talks about multi-frequency periodograms and writes down a general formula and so on. So this idea has been around for a long time, but as far as I know, nobody has developed an actual turnkey explicit algorithm that you can just plug numbers into for it. Larry Bredhorst, for example, has some results in his wonderful book. I don't know if you know his book, that, by the way, is freely available on the internet with the publisher's permission, unusually, I guess, but has some really neat stuff. But so this whole, what I've tried to do here is to take this idea that's been sitting around for a long time and actually provide a turnkey algorithm. I'll skip over this. There's a lot of criticisms of LSP, and I have answers to all of them. I'm not. I want, in view of time, I guess I should pay attention to that. Okay, we're getting there. One of the ones that isn't mentioned too often, but it's often stated, oh, the LSP is based on a single frequency sinusoid, so you can't use it for anything more complicated than finding single periodic signals and so on. But the statements like that are not typically followed up by an explanation of why that's a limitation and what problems that cause. In usage, people ignore that and think of the periodogram as estimating the power spectrum at all frequencies. Maybe the term is statisticians call it a scan statistic or something like that, and you simply scan in frequency and it tells you what is going on at that frequency. So it is an estimate of the the true power spectrum. But wait a minute, the model is a sinusoid, it's a monochromatic signal. So what's going on there? So I don't know. I think that's a lot of that's semantics and can be clarified. But so what I looked at was taking a two-sinusoid model. The thing at the top is a obvious extension of the.
Can I interrupt for a moment, Jeff? So, this whole periodogram thing is a linear theory, right? So why do you actually need more than one frequency?
Oh, it's not linear. The Fourier transform is linear, but the sorry, that's I don't know if there's any slide that shows it, but it's not. The periodogram itself is a square.
Right. Okay, sure. Right.
It's nonlinear in the frequency. So if you think of it as a parametric inference problem, it's linear in the amplitudes, but nonlinear in the frequency.
Okay. Yes. That's.
Okay.
Okay. Well, here's a kind of a messy slide, but at the top is the two frequency model. It's a mistake not to have the Lomb shifts with subscripts because they're different in the two terms. Apologize for that. But so the first thing I did was to take this model, evaluate the log likelihood or the mean square residual or whatever, and do a straightforward maximum likelihood, or just minimize the residuals using symbolic algebra. And I used MATLAB system and so on, and turn the crank, and you get an expression which I'll show later. But all along, I thought, well, probably a better thing to do is marginalize the likelihood. Larry talks a lot about that in his paper, and in fact, a lot of what I'm going to show is really essentially following up what he mentioned. And there's sort of a cute trick that at first I thought wasn't going to work out, but you can actually exactly evaluate the integral, the marginalizing integral of the likelihood for over all four parameters by a simple iteration of this Gaussian integral. The key is that if you start just doing this integral with respect to the first amplitude, you get it's of this form. It's an exponential of a quadratic form. And applying this formula, you get what looks like it could be a mess, but the capital A in the exponent is just a constant with respect to the parameters, the b's. So that integral is in turn an integral of the exponential of the quadratic form. In other words, of the same form. So you can even, I used MATLAB's symbolic algebra expressions to just write down a simple few line iteration of this integral where you're just extracting the coefficients of the argument of the exponential at each step, and I'll show the results of that in a second. And by the way, in all of this, a really interesting thing is that you don't need to have the sines and cosines as the basis set, so to speak. There's a lot of work by I'm not sure how to pronounce it. The Balyev, I think he's a Russian. He has a lot of nice papers, and he proposes this this basis set, which is similar to the cosines and sines, but it has a different behavior at the singularity when the two frequencies are the same. And I hope I get a chance to mention it, but in what I'm going to show, there's a little problem with that case where when the two frequencies are the same, there's some denominators go to zero and you have to fudge that. But So,
So because because it's linear in A and B and you're marginalizing just over those, there's a known relationship between the marginal and least squares. So
Yeah.
it should basically get the same answer, except I think there might be mul multiplying it in the front. There's a more slowly varying Jacobian type term from doing the orthogonalization when you marginalize. But
is that, but that surely that depends on what the priors are. This is based on,
yes, yeah, this is for either a flat prior or a conjugate prior.
Gaussian, yeah. Because when omega is known, which is what you're doing, your omega isn't obviously known, but you're integrating with fixed omega. This is Gaussian linear regression. So all of the posteriors are available in closed form,
okay, well, that's,
which is what you're doing here. Yeah. And
and
so the ones at the bottom also, because there are different versions of the covariates in a linear regression.
uh-huh.
And when omega 1 is equal to omega 2, it's like you're doing a regression with the same x variable twice. It's the same predictor variable and trying to decide which one is the important one. And that, of course, is impossible.
Yeah, well, maybe you have an answer to, at the end, I'll show some challenges that I'm facing, but maybe that's an answer. But let me go ahead because
Sure, yeah.
this is just a little more detailed using Larry's notation and so on for expanding things in terms of a general. I don't know if there's a name for it. I've invented the name omnogram because what you can calculate is a periodogram formula that you can, if you have the sine and cosine basis, you just plug in your data and you get an answer. But for any basis functions of anything, they don't even have to be orthogonal. Larry has a whole section orthogonalizing the basis functions. And at first I thought that was necessary, but in fact you can carry out the marginalization without orthogonalizing the basis functions, unless I hope I'm not.
No, that's right. Yeah.
But anyway, so you can get a really general thing, which so here's what the nitty gritty. These are the things you need to stuff data into. These are sort of MATLAB, pseudo MATLAB notation where you have two frequencies, omega, which is omega 1 and omega 2, and the terms in red are the analogs of the Lomb terms that you throw away by orthogonalizing those two things. And you can do the same trick in this general expression. And so here's what you get for the least squares, or the maximum likelihood or least squares solution. You get fairly messy expressions, but you can separate them out into things. The DGs are things that involve the data. Everything else just involve the sines and cosines. I think of them as the trigonometric terms. So if you happen to have cases where the sampling in time is the same and you're going to have lots of different measurements at those same times, you can pre-compute most of this mess. And just I don't even have to write out an explicit formula for the double periodogram. And you just paste these results from the symbolic algebra script into a running code, and evaluate these things and stuff it into here. So the explicit formula for the double periodogram here would be a horrible mess. The Bayesian thing is a little simpler. I don't know if this is simpler, but anyway, here's the result is just a numerator over a denominator, and it's the denominator that I think goes to zero along the omega 1 equals omega 2 line. So that's a bit of an issue. But so anyway, Tom, you said should be equivalent. These two should be equivalent. Can you look at these formulas and tell me?
Yeah, I don't.
You say, I'm sorry, what's the case when they're equivalent?
Oh, Tom?
I was saying that when you do for a linear model, doesn't have to be sinusoids or anything. For a linear model, when you profile, you get the same result as doing the same model with a flat prior and
Yeah.
marginalizing.
Yeah, the posterior mean is the same as the MLE.
Yeah.
So that's right, yeah.
Yeah.
Okay, great. All right.
One thing to say here, Jeff knows I wrote a paper doing something similar in the audio literature many years ago, but is this looks like a mess, but it kind of hides an important computational thing here, which is that the double periodogram doesn't use anything that's not already in the Fourier, the projections against sine and cosine, which are basically, if it was evenly spaced, they'd be the Fourier transform. So what happens is there's a real and an imaginary part, or a sine and a cosine projection when you compute a Fourier transform. The Schuster periodogram combines those two things in a particular way. You find the magnitude. The doublet and other multiplet periodograms just use the same transform, but combine things in a more complicated way. So you're not having to compute different projections. You're just evaluating the same Fourier series at different frequencies and combining them in a different nonlinear combination than just a squared magnitude.
I don't think that's right, Tom. That there are cross terms. Maybe I'm not understanding.
Yeah, that comes from multiplying to the same Fourier transform, but evaluated at different frequencies.
Okay, I'm not sure exactly what that means, but the same.
So what I'm saying is you compute your projections in equally spaced data. It would be just the Fourier, the DFT, and you have you then have two things that are functions of frequency on a grid, and the doublet periodogram uses just those two things, but evaluating them, taking an interesting combination of the real and imaginary parts at different frequencies.
Okay, great. So at the end, one of the questions or open questions for me is there something that could be called a two-dimensional Fourier transform and this periodogram is the absolute square of that Fourier transform. Are you saying yes to that?
No, I would actually kind of say the opposite, that the information, so distinguish the power spectrum from the Fourier transform. There's information that's lost when you compute the power spectrum that's still in the Fourier transform, and the multiplet periodograms pull that out.
I don't know about that. There's phase information that's lost in the double periodogram, isn't there?
Yeah, I'm not saying all the information in the time series. Obviously, it's model dependent. It's assuming a basis function and doing projections. So information is lost, as it always is when you do a projection. But what I'm saying is, for this purpose, for multiple sinusoid models, the information is all in the Fourier transform.
Okay.
And this is just combining values of the Fourier transform at different frequencies in a way that's different from the power spectrum.
Okay, that's I think I get that. There's cross phase information and there's other phase information, and is that correct? And the cross phase information is preserved, but other phase information is lost in the periodogram. Maybe, I don't know. Well, sorry, let me.
Yeah, just go on. Yeah.
I'd like to show some astronomical results. I showed the sunspot data, but this is a simulation. The first thing I did was to see what happens if you generate two sinusoids and make them close together. And the upper left which I think should be known in the literature as the Swedish flag diagram. I think it's very similar to the Swedish flag, if I'm not mistaken. But anyway, how do you interpret this double periodogram? Well, the first thing you would think is do the same thing as you do an ordinary periodogram, find the peak, and then do profiles of that peak to see what's going on. And so it's straightforward. Here's the maximum of this double periodogram for the case of two sinusoids. Here are the two frequencies in a frequency space. And if you project them in one direction, you get an accurate determination of the frequency of one of the components and the other. When I first did this, I had no idea. I kind of expected these profiles to be sharp, to be really sharp, but they're not. And in retrospect, that was silly of me to think that. They're just as broad as, they're essentially one-dimensional periodograms focusing on a part of the data in sort of a mixture model type of scenario or something like that. But anyway, the point is that you can accurately determine the peaks of these broader profiles. They're two separate profiles, and they get the correct frequencies. Whereas the bottom right is an ordinary periodogram that doesn't even show two peaks, and so you have no hope of resolving because these two frequencies are closer together than the Rayleigh criterion. So let's study this as a function of the separation.
Sorry, quick question there. So is there a way to, so for instance, if you suspect that the real data has two frequencies, is there a way to test whether it has those two frequencies, or should you stick with a single periodogram?
Great question, and I think I'll answer it in a few slides. So
okay, sorry, go ahead.
So here's just some more simulations. Here's a noise-free infinite signal to noise. I guess I shouldn't have been surprised, but you have unlimited resolution in the sense of separating sinusoids, no matter how close together they are. This is a plot of the estimated frequency separation divided by the fundamental, so it's kind of like a Rayleigh fraction or something. It's unlimited. Of course, in practice, well, two things. This is for a function of the length of the time series, and at some point, even for infinite signal noise, it has to break down at the low end. And you also recover the amplitudes. There are four separate amplitudes, and you at zero separation, of course, there's no way there's no possible way to separate the four different amplitudes. But once you get any separation at all with infinite signal and noise, you nail the amplitudes of the components. But of course, we never have noise-free data. So here's a pretty high signal to noise, 8 to 1, so to speak. You still get really great tracking of the frequency separation, well below the Rayleigh limit. And after a little bit of uncertainty, the amplitudes get nailed. Here's signal to noise 1 to 1. Things are getting a little dicier. You still get excellent frequency resolution. The amplitudes are a little sketchy, but in the end, of course, you get the right ones in some sort of limit. And here's even worse signal noise. Amazingly, you still do pretty well in the frequency separation, although the amplitudes that come out are kind of squirrely. So anyway, here's what happens with the sunspot. Remember, I showed the thing at the top before. Here's what happens with the double periodogram. Here's the diagram. And you see a pretty clear indication. In some sense, you can look at only the lower right of this diagram. There's a symmetry. It's not exact symmetry because of end effects, but in essence, it's symmetric. So, and the peak is here. Oops. And if you do the slices in the vertical and horizontal direction, you get these two pretty well separated peaks that give you two cycles. So
So in that case, so the idea generalizes. I mentioned multiplet periodograms earlier. If there's more than two, there are actually settings where it pays to have a three-sinusoid model.
sure.
Is this one of those, maybe? Is this just a double periodogram?
Good point. I haven't tried. As you might imagine, the three frequency one is even more complicated. But actually, I ran the code for 5 frequencies, and it generated a result that didn't explode my computer. The text string representing the solution is a enormously long thing, but computationally there's no problem with it. But in interpreting it takes a little. It took me a while to figure out how to interpret these two-dimensional plots, interpreting 5-dimensional plots or something. But no, you're absolutely right. You should think about higher orders.
Can I ask a question? I mean, sorry, what's going on with the peak to the far left that you haven't labeled?
I don't know.
So is that the reason, Jeff, or I'm sorry, Tom, we think that there might be a third, what do you call it, period?
Yeah, I'm just looking at the doublet periodogram above it. It just looks like there's a lot of structure that I haven't typically seen when I've looked at doublet periodograms. So.
This one is a singlet. This is an ordinary.
No, I meant the color. Color.
Okay. Right. Yeah, no, I think that's right. I think the blue line and the red line are the maxima, sort of blindly taking the maxima in the two slices, but there's a secondary maximum that you're right. It's maybe something's going on. So one should do a triplet. Sure. Let me go on to, I think this answers Vinay's question. Here's there's some nice data that I got from the authors of this paper of pulsating white dwarf. I don't show the light curves, but it's really nice data. And the power spectrum, single frequency power spectrum in blue with the point spread function for, this is a LSP of this data, showing a bunch of obvious frequency components that I guess are understood to some extent in terms of pulsation theory for white dwarfs and so on. But the question is, are any of these doublets? And I think, Vinay, that's what you're asking. Is there any reason to believe that these that any of these peaks are not really singles but doublets? Well, there's no physical reason, but I set out to answer the question. Suppose I do a 2D periodogram. What shows up? And here's what shows up. Here, this is a broad showing not the full range of the that I showed before, but a restricted range. And first of all, there are two frequency axes that I haven't labeled just to make the figure not too busy, but X and Y are both frequencies. I didn't draw a diagonal line. I draw it at the corners, but because that's the singular line where things are a little dicey. And these plots are made with a simple hack of interpolating across that singularity. When I looked at the numbers, these things didn't have any fine scale structure across the singularity, so it looked like interpolation was okay. But I guess David is going to tell me how to get an exact solution to what's going on at the singularity, and I don't know, maybe
now the solution is to drop one of your covariates.
Well, I did that, and anyway, there was something that puzzled me when I when I played games like that. It looked like I get numerically, I just got different numbers. I looked at very close to the singularity. And in fact, actually, I guess this addresses it. The white line at the bottom is a trace along the diagonal using my interpolation scheme. And it's essentially like a 1D periodogram of the data.
Exactly. So along the diagonal, it seems to me what you should see is the 1D, because then they collapse into one sinusoid.
Right, but that's the point. It's roughly the same, but it's not exactly. And when I replaced the 1D periodogram along the diagonal, there was a discontinuity in the result. It's not exactly the same. So maybe there's a factor of 2 that I screwed up, or 2 pi or something.
Some numerical thing even.
I played around.
I have a vague recollection of this, that I mean, the way I formulated this problem was the orthogonalization that Larry worked out. And so I think there was a Jacobian factor that's in the front. So you get some factor and then an exponential of what looks like a kind of least squares double periodogram, but I think the Jacobian in the front might have trouble when the model is not identifiable. I can't remember.
This is great feedback and so on, but let me go on.
Can I ask a quick question here? So every one of these spikes or maxima that you see here, they seem to be harmonics of existing pulses, right? I mean, is that the way to interpret it?
No, well, there's one harmonic hidden in here, and that's the next step. Here's here's the line of where the 2 frequencies are the same. Here's the locus of the second frequency being twice the first frequency. And so you look for where that shows a peak, and there, in other words, this identifies a potential harmonic, that if the frequency on the omega 1 and omega 2 corresponding to that point are in the ratio 2 to 1. So this picks out a harmonic. Maybe it's an accident because there are so many frequencies. I don't know. That's sort of an astrophysical question, but you can think of this as a scheme that allows you to find harmonics, but that's sort of trivial. You can go, if you have even a fairly large number of peaks, you can look for factors of 2 without doing this rather expensive computation. So the question,
when I was doing this with simulated exoplanet data for SIM, I found it helpful to plot it as a function of frequency 1 and the splitting, rather than the 2 frequencies. And then some of the patterns kind of become more straightforward to interpret. I'm embarrassed that I didn't read through that paper of yours carefully, but I know you didn't. You've done stuff that you haven't published and so on. But I'm talking about stuff that's just been in posters.
I feel awkward not giving you more credit in my paper eventually.
No, it wasn't. The only paper on it is in the audio signal processing literature, so I don't know how you would have ever found that. So
but it's fairly, with all due respect, it's a fairly sketchy thing, if I remember. It doesn't go into details.
What you call details, I call the trees instead of the forest. But like it points out the connection between the discrete Fourier transform and how you can interpret it, in terms of reusing that instead of just computing the power.
Yes, well, all of that. Okay, well, okay, great. Anyway, here's on the left is a little study of similar to things before, where I take two frequencies and embedded in the actual data for the white dwarf. I was a little nervous about using simulated data, even adding noise. It's not as realistic as signals embedded in real data. So here's a study where I vary the separation from half Rayleigh to zero separation to see what happens in the 2D plot. And here's one of the peaks in the white dwarf showing that its peak, which you can't see too well because of this isn't a very good plot. But anyway, the peak is the red dot, and it's right on the equal frequency line. So this is negative result, negative information. It says, no, this particular peak is not a doublet, it's a single frequency. So Vinny, I guess I'm not answering your question because I didn't give you a prescription for knowing ahead of time whether to do this business, but
Well, even post hoc, I mean, if you can make a decision,
yeah, well,
you can test whether you need the two frequencies or not, right?
Well, they're nested models, right? So you could do a likelihood ratio test.
Right.
I mean, that would be a much not like that white dwarf where you have all of those signals. I think it would be quite complicated. But if you have, like the sunspot one, I suppose you could try to test if there's a third peak.
But it's going to be the same issue that you guys found with lines where the models become non-identifiable and you have to worry about. So you could do a likelihood ratio test, but you can't just use Wilks's theorem, probably.
Oh, right. Yeah. You have to worry about the null distribution. Exactly. Yeah.
Okay, well, let me jump ahead. Here's sort of the end of the first part. Anyway, here's the things that I'm still wondering about, and we've talked about some of them, but love to get more applications. As I think astroseismology is full of potential closely spaced frequencies. Fixing the singularity with a principled solution instead of a hack that I used is
quick question about those singularities at omega 1 equals omega 2. So in the value formulation that you had, Jeff, there was effectively sine delta omega over delta omega term, right?
Yes.
That has a limit.
Yes.
Delta omega equals 2 and basically drops out. So isn't that a simple way of figuring out what that solution should be for that particular case?
That's what I thought, but and I did it, and I'm trying to remember, it didn't do very much. I forget the details, but I think it wasn't a magic solution to.
Yeah, I think it's just linear algebra. If your space is spanned by two vectors, you can't make up four vectors and identify them all.
No
transformation.
Oh, it's an identifiability.
It's still in a plane, right?
Yeah.
Okay. So here, this Fourier transform thing that I was getting at with Tom, I don't even know if this is a meaningful question, but is there something you could call a two-frequency Fourier transform that simply has the property that, it somehow has some Fourier transform-like properties, but its absolute square is these periodograms that I've calculated. Is that possible? Because it's true in the one-dimensional case, I showed my Lomb-Scargle Fourier transform that gives you the Lomb-Scargle periodogram. And is there any limit? Can you take the limit of an infinite number of components and get something? Is this meaningful in a periodogram for a frequency continuum? Does that make any sense? I don't know.
So I think that's probably related to the Whittle likelihood.
Okay.
That's actually a good question. But so the Whittle likelihood shows that the Fourier transform. So with Lomb-Scargle, you basically show that the Fourier transform is a sufficient is all you need to, the power spectrum is all you need to know to do least squares or Bayes with a single sinusoid model.
Right.
what Whittle showed is that there's actually another model where that's also the only thing you need to know from the data, and it's a Gaussian, stationary Gaussian process with where you know the power spectrum. So there's some relationship there. It's not, he didn't do it the way you're talking about, like, is there a continuum? That's a very interesting question, I think.
Okay, and then let me just quickly go through these last two are these sort of tidbits at the end. Bayesian block histograms, the algorithm can be used for event data, and it's equivalent to doing a histogram. It's a data adaptive histogram. A lot of people, I don't know if many people do it, but you have to remember there's a penalty constant. I guess you call it a regularization constant, or anyway, it's from the prior on the number of blocks or bins. And here's a scan. Here's some data from it's some period ratios in exoplanets that, I mean, Tom may even know the data. But anyway, if you scan the penalty constant at one end, you get a lot of, in fact, if you go further down, you find you essentially are giving each data point its own block, its own bin. And at the upper end, which isn't shown, the entire data set is one block. So you have to remember that this constant matters. And people often just use a default that's written into the code. They really should play around with it. And anyway, what's new that I've developed for the book is that the original algorithm does not permit a block or a bin to be empty because it defines blocks to start at a data point. A block has to have at least one data point, but there's a generalization that allows empty bins, and that's shown here. And it turns out, I thought maybe this is a possible resonance that might mean this bin is empty. But in doing this, I suddenly realized, and Tom, you and Phil Gregory solved this, but this ignores the uncertainty in the measurements. The algorithm takes care of the uncertainty in the counts in the bins with the Poisson model. But to ask the question, is there really an empty interval around this resonance? Clearly, the errors in the measurements matter. And so there should be a generalization of this that takes into account those errors. I discovered, I think this is right, and I don't know if this is well known or not, but convolutions can be, there's a convolution group. These things I call filters or autoregressive coefficient vectors, or whatever you want to call them, moving average coefficient vectors. There's actually, you can define a group, and the sticking point is the existence of an inverse, convolutional inverse, and there's a way that you can, with a little restriction, you can make sure that every filter has an inverse. And this underlies a relationship that I think is not fully appreciated, namely that all of these models are equivalent to each other. Any stationary process by the Wold theorem can be represented in his formulation. It's a moving average, but any moving average can be converted to an autoregressive or an ARMA. And there's a way of defining the ARMA models as a group, not just the convolution group, but the ARMA models form a group. And that leads to well, let me skip this. This is deconvolution of non-causal moving average representations. And I think it's really neat stuff, but it's a little bit off point. And I want to get to this. This is a plot from an old paper, 1926, from Udney Ewell, the famous Ewell of Ewell Walker. I don't know, David or Tom, you're the most likely people to know of this paper, or maybe I've.
No, I don't know.
Okay.
I don't know. I'm quite curious about it though. It looks pretty cool. What is he plotting?
Okay. The time series, the time in years is the horizontal axis. There are two data sets. The line is one data set. I've covered up what they are, so not to bias you. The circles are another data set. And the question is, are these data correlated? So I'm not going to embarrass anybody asking for an answer,
Yes.
but let me uncover what they are. The the circles are the mortality rate in England and Wales per thousand people as a function of time. And the line is the proportion of Church of England marriages per thousand. Oops, sorry. What have I done? Let me go back.
Yeah.
Maybe this is nature's way of, there we go. So, and I love the final, here's the, to me, this is one of the most amusing things in all of statistical literature. I suppose it is possible, given a little ingenuity and goodwill, to rationalize very nearly anything, blah, blah, blah. And he poses a potential, I mean, this sounds almost like a political posture that we see on the news every day. But most people would, I think, agree with me that the correlation is simply sheer nonsense, not just nonsense, but sheer nonsense. So, and in fairness, I think this is relevant to a lot of.
They are correlated but coincidentally or unrelatedly or related to some third factor. To say it's a causal relationship is nonsense, but I don't know what it means to say a correlation is nonsense. Correlation is the sum of x times y times, divided by the sum of the squares of x and the sum of squares of y.
Yeah, what he's saying.
It's like to say this mean is nonsense. I don't know what that means.
Well, parsing his words, he says it's a nonsense correlation is in the title. It's a correlation, but it has no sense. It has no meaning.
Well, I think he's doing the classic confusion between what David is alluding to between correlation and causation. It's assuming a causal relationship because of the correlation is what's nonsense. The correlation is real. It's just a number. Right?
Well,
you can do a pretty good job of predicting one variable from the other.
I disagree because the point, my interpretation of the point is that if you have two things that are varying, no matter what, if you focus on some interval where the variation in both of them is fairly smooth, you're guaranteed to find a fake correlation because either they're both increasing or one's increasing, the other's decreasing, or they're both decreasing. And
so that's like saying if you have a process with mean zero and you look at x bar and it's not zero, actually zero, it's nonsense. I would just say it's noise.
I think it's a matter of interpretation of what you mean by whether a correlation is real or not. In the big picture, the correlation was guaranteed by the smoothness of the fact that two varying quantities. No matter what those quantities are, they could be completely unrelated causally. You guarantee that there is a apparent correlation.
Right. But I mean, maybe you just need another word for it, but it is a handy thing to know that two variables vary together. And we usually call that correlation, and that's distinct from causation. But if correlation has to have a causal or scientific relationship as well, then we would still need another thing, which is just looking at how two variables happen to vary together. For prediction purposes, for example.
Yeah. So I guess it's worth noting, I was just trying to look up, like, what does Oxford say the word correlate means? And it says it means to have a mutual relationship or connection. And in that colloquial sense, then Jeff is right. And Yule was right. It's a nonsense correlation, but that's just not the way the term is used in statistics. It has a more precise meaning.
Yeah, help me out. We need a new term for something that's not exactly what we're talking about, but what is the most general term for some connection between two random variables? The terms covariation and correlation and mutual dependence and things like that are all co-opted for specific things. But what is a very non-committal statement that the two things are not completely unrelated to each other? What should we call that? The two random variables
Well,
are what?
even with my description of correlation, it's still not a completely general relationship. It's a measure of linear relationships, right?
Yeah, but
One variable varies linearly with another. So beyond that, I mean, it's just, well, I don't know.
because I'm trying to dig into things beyond linear correlation, of course, and they're like the copula and dependence measures and stuff like that. And I keep getting hung up on just trying to wordsmith something that refers to completely non-committal question about are the two variables connected in any way? I mean, that's kind of the phrase, or connected variables maybe is a phrase. I don't.
Now, I mean,
Dependent.
if you say two variables are independent, that means that their joint distribution is the product of their marginals.
Right.
So not that says that the conditional distribution of y given x depends on x in some way. But it can be any way. So dependent random variables are, like not independent. The conditional distribution of one variable depends on the other.
But that's still too specific for what I'm after. It's dependence is a very specific thing, which you just nicely outlined. But
dependence doesn't mean anything like causation.
I know.
Or even directional. It just means that they're not independent. That's all that
It
it
means
means.
knowing one helps you say something about the other.
Yeah.
Yeah, those are all nice, specific things to say. But I guess maybe it's my question is not well defined. But I want something that isn't specific to any measure or any concept of relationship, but
I looked in the thesaurus, and some of the options are associated, linked, related.
yeah. Associated is close. I think it's of all the things I know of, associated variables is close.
Linked is
Getting off. Anyway, thanks for all your comments, and Tom, I really need to like I said, to focus on, I don't know, the status of that paper. By the way, I've submitted to APTE letters, and Tom, if you refereed it, I think I will know when I get.
No, I haven't.
Since I submitted it, I've found a better. I don't know. It's nothing new, but I've reorganized it. The appendix is completely different and so on. So it's in progress, and I want to add more deference to your work, but I'm not sure how to do it since a lot of
Don't worry about it.
it's not.
Oh, well,
worry
you
about
can
it.
always, when it comes back to you, you can always add citations. That's not, no referee's going to complain about that. I guess unless you well, I'm not in this case, but in general, if you add a citation that is like where the work was done before, that might upset a referee. But
Well, as far as I know, no one has simply turned the crank to existing formalism starting back in that Barning paper. I mean, he doesn't actually write out enough so you could do it by turning the crank. He writes down an infinite sum over an arbitrary number of components and says, and even Lomb's paper talks about that. So the idea isn't new at all. And
Yeah.
this guy Laredo has done some things too. So
No, but part of why I didn't write it up is because I was under the impression, and I didn't do some significant literature work is I thought this had to be not what you've done. What I was doing had to be kind of implicitly in the harmonic analysis literature, not harmonic analysis in math, but the harmonic analysis. There's the time series literature is so kind of bifurcated or trifurcated into different pieces, but there's stuff on harmonic analysis there that I must be related, and I just never did the work to mine that literature.
So
Jeff,
I have one more comment, and this is, when I was looking at the images, it reminded me about the talk by Rebecca Phillipson, who's done some recurrence analysis, and she made, several plots for X-ray binaries and AGNs, where you look at variability, which is stochastic, but you can also identify periods. And I'm wondering if there is any relation between the two, because recurrence in her work is more general than just periodic, because you can apply to noise data and different systems. I can send the reference.
Oh, yeah, thank you. Just say a little more about what she did. What is it?
It's recurrence. I don't know details of the mathematics, which she was, but she was making the plots where you could identify the eras. I mean, two-dimensional plots where you can identify plots related to light curves, and you can identify the periodicity and the behaviors in characteristic frequencies in those plots. I will send you the reference because I don't remember details at this moment.
Okay.
But it was interesting case and it may be relevant to some ways. So it's Phillipson, I think.
Yeah, speaking of references, when you had mentioned astroseismology earlier, that reminded me that I was once talking about this doublet periodogram stuff with Brendan Brewer, and he told me about a paper of his that I'd overlooked that does Bayesian kind of periodograms for astroseismology. So I dumped a reference into the chat. So, and I never read the paper because I wasn't working on this stuff at that. We never got our funding for it, but he did tell me that he was disappointed that it didn't make as much of a difference as he hoped. So made me wonder what was going on there. Maybe he wasn't doing the thing correctly. Maybe it really just didn't make a difference for the particular data sets he was looking at. But anyway, it looks like they don't have a big paper on it, just some short papers.
Okay, that's great.
Jeff, one question about the sunspot analysis that you did. So you found these two very closely spaced frequencies.
Yes.
Do you have the beat period? I mean, when do you expect them to cancel out so that there are, so the sunspots go to zero?
Good.
And is that consistent with the Maunder minimum?
I never looked at that. But my excuse is there are probably three, so it's more complicated. No.
Well, multiple beat periods, yes. There must.
That's a good point. I don't even the two periods were, in the same ballpark as what people toss around for the solar cycle. But I guess naively, I thought that what I was going to get was a nicely well-defined single peak at the solar cycle. And I looked in the literature, and it's amazing. Almost any statement that you can imagine to make about a power spectrum is made about the sunspot number power spectrum. It's complicated. It's multiple. There's subharmonics. There's harmonics. It's a mess. I don't know. Does anybody here know work in that field or know what's going on? What the current understanding of the
Well, I do. I have done some work on sunspots. There's a lot of purely statistical work as well as models that claim to use some physics. It's complicated. It's
Yeah.
anyway. So now we are well past our time. So thank you, Jeff. It was a very interesting discussion.
Yeah, that was a lot of fun.
Yeah.
Yeah.
Definitely.
Thank you.
Really.
Bye.
Thank you.
Oh yeah,
Thank
we
you.
need to
Yes, we should.
Bye
Thank
bye.
you. And I guess this is our last meeting of the year. We'll try to catch up again in January, I guess.
2026.
2026.
2026.
Sounds good.
As a
Okay.
bureaucratic
Bye-bye.
thing, is it possible for me to be added officially to the CHASC?
CHASC. Absolutely, yes. Yeah, I'll do that. Go ahead and do that right now.
Sounds
All
good.
right.
Okay. Bye-bye, everybody.
All right. Yeah. Bye.
Thank you. Bye bye.
Oh, bye, Sarah.